Welcome to the Global Composites Experts webinar series. My name is Wenbi Yu, Director of the Composite Design Manufacturing Hub. This webinar series is to examine the history, present capabilities, and future of composites with the goal of sharing the knowledge of composites that has been developed over the past 50 years. This webinar series was initiated by the Composite Manufacturing and Simulation Center at Purdue University. We are located in this beautiful Indiana Manufacturing Institute. All of you are welcome to visit us when life returns to normal and it is safe for us to travel. We launched the CDM Hub in 2013 with the mission to convene and serve the global composite community by creation, education, evaluation, and sharing of resources for composite design and manufacturing. CDM Hub provides a very powerful website called cdmhub.org for the composite community to carry out this mission together. We envision CDM Hub to become the premier resource for composite design and manufacturing in the near future. This webinar series is one of the initiatives CDM Hub started as a service to the community. This webinar series is made available by the support of CDM Hub sponsors, including Dassault Systems, SciTech Survey, MAC Software, and Modex 3D. We greatly appreciate their financial support for CDM Hub. Next, I will show a brief commercial from one of our sponsors.
In case you are wondering, you are not fighting molding defects alone. Introducing Modex 3D, your plastic injection solution. With powerful molding simulation features, friendly and easy-to-use interface, Modex 3D pinpoints design problems before production and achieve better product quality with less time, less cost, and less waste. Modex 3D, the best partner for plastic industries.
Thanks again for our sponsors' support. We invite more organizations to join them to serve the global composite community together. This webinar will be recorded and made available on CDM Hub. An email will be sent to you once the recorded video is available online. The presentation will last about 40 minutes and will have about 15 minutes for Q&A. All attendees are muted. Please submit your questions through the Q&A box. After the speaker's presentation, your questions will be read and answered. And next, let me introduce our distinguished speaker, Professor Reddy. Professor Reddy is well known in mechanics of composite structures and materials. He is the author of 18 textbooks in mechanics and the developer of shear deformation series in the plates and shells literature that bears his name. Reddy third-order plate theory and the Reddy layer-wide theory. His name now belongs to the company of Origin, Mindlin, and Coiter. In recognition of his achievements, he was elected to the National Academy of Engineering. His work has received more than 81,000 citations and has brought him an H-index of 112. Professor Reddy received many prestigious awards, including the most coveted Timchenko Medal and ASME Medal. Professor Reddy is the O'Donnell Foundation Chair 4 Professor, the Regents Professor, and the University Distinguished Professor, and the Director of the Center of Innovation in Mechanics for Design and Manufacturing at Texas A&M University. He holds the PhD in Engineering Mechanics from the University of Alabama Huntsville and the Master degree in Mechanical Engineering from Oklahoma State University. And Professor Reddy, we are looking forward to your exciting talk. Please.
Thank you, Wenbin. Appreciate your comments. So So very good morning to all of you. Some of you are in regions, so I believe it is good evening. In any case, I will share few of things that I've been doing for past few years, especially in the areas of development of robust shell elements as well as non-local mechanics, in particular about non-locality in assessing damage and fracture. So these are the two major topics of my presentation today. And I will go on to say a few things toward the end of my lecture in the way of, I would say, remarks, so that some of you may agree or disagree, but I think it is something that we need to share, understand our role in the engineering community, especially the mechanics has been not at the forefront of many things for some last few years, maybe even more than a decade. Materials has taken the lead role, which is fine, but we have to work together. Mechanics has to have its due role in assessing materials in situ, that means in the actual working conditions, because material science only can address certain aspects of the behavior, but mechanics is the ultimate certification role in doing their job. That means materials functioning in a right conditions and also functionalities being met. So with that remark, let me go on to show my roadmap for the lecture. I will just say a few more words about the works that I'm doing. And I will begin with the first robust shell element, and I will explain why such an old topic is still being pursued in terms of research. Then non-local. The non-local, there are two parts. One, I will say more in the introduction of the strain gradient and modified coupled stress models. But I also will take enough time to discuss my latest interest in GraFEA, graph-based finite element analysis, which piggybacks on the traditional finite elements. So that means we don't develop a new finite element model, but introduce non-locality into the existing finite element network, and I'll say a few details toward the during that topic, and close with some remarks. So first, let me get back to the main thinking that I have come up with in the last few years, especially after seeing all these various models advanced by different colleagues in pursuit of improving the mechanics models, taking them into practical arena in terms of providing the ability to the real world in determining the ultimate damage and fracture, and assessing functionalities in the context of applications. So, but I want to remind everyone, we continue to develop these models. So everything we do is really modeling. Means there is nothing like an exact science. We never will get there because it is a infinite convergence process. But everything that we do in the next step is a better model of the previously developed. So that means we still ride on the shoulders of our colleagues who have already contributed. We continue to contribute greatly to the improvement of these models. And so the shell element, as many of you know, those are in commercial codes. They are being used, but they still have limitations. So this is where my comment regarding improving the models come. So it is in that pursuit that we have spent quite a bit of time in the last decade or so. So the main features will be to improve both mathematical model and finite element modeling, meaning converting the mathematical model into discrete equations, avoiding the use of any fixes. So when I use the word fix means as engineers, we are really focused about solving the problem. We are problem solvers. In the pursuit of that objective, we at times tend to bring some tentatively maybe some fixes such as stabilization, Reddy's reintegration in computational fluid dynamics, artificial viscosity, upwinding, and so on. But these are really not germane to the actual physics. Those are only computational fixes that seem to work for the goal you probably have, but sometimes you don't realize that they have side effects. Just like any medication anyone takes, it is not tested with every individual in the world. So it will have different side effects to different people. In the same way, these fixes may have different side effects in different applications. So it is better to avoid them if possible. So if at all not possible to eliminate totally, we need to still pursue what is that it is doing, what is the side effect. So one simple attempt here is to eliminate those fixes and all types of locking, while keeping the efficiency in the form of computational effort and accuracy. So the work that I've been doing for a while has been really helped with, contributed by my students. All three have graduated, and I consider them to be the lords of shells. They have worked for a long time in helping, at different stages of this development. So Roman Arciniega is from Peru. He returned there to serve on a faculty of the University of Peru. Greg Payette is at ExxonMobil Research and Development. And Miguel Rivera came from Mexico, and he returned to serve on the faculty there very recently. So my first thing that I'm trying to do is to incorporate, because the traditional shell elements are all plate and shell theories, going even back to mechanics of materials discussion of whether it is a classical or shear deformation theories, we assumed or presumed that the thickness does not change. We made the assumption of the transverse material lines through the thickness remain inextensible, straight, and depending upon the classical or shear deformation theory, it will rotate or not rotate to stay perpendicular to the tangent line. So we were able to eliminate this restriction of the normality, and we have accommodated shear deformation in a satisfactory way without wasting too many degrees of freedom. So, but one thing that we have not done enough is the thickness stretch. So the key element here is if it is a finite deformation. So please understand in the context of what I'm speaking here. If it is not finite deformation, it may not be significant in terms of the thickness stretch. So what I'm saying is if you start with a plate or shell element, what you do is when it is being stretched, the material has to flow from thickness into the in-surface. And that is what I'm talking about. Even when the thickness does not change too much, but saying that it is an inextensible creates an artificial stiffening effect in the computational model. So that is the main issue. So let it go, do whatever it needs to do. So that means we have to bring the thickness Poisson effect. Okay. So, and I won't go into the inner details of these. These are shell theories that are available in the literature, but I only point out that I have added in the expansion of the displacement field, the in-plane or in-surface displacements, 3 of them. Then rotation variables, 3 of them again, including the drilling degree of freedom. Then we bring this vector, but it has only one component, namely through thickness. So that is the thickness stretch, and xi superscript 3 is the thickness coordinate. So you know that it is a square. Means the thickness stretch is really represented as a variable attached to the thickness squared. As a result, you will have the epsilon 3 if I use the third dimension as the thickness coordinate. So in other words, you will have all 6 strains non-zero. So this will require us to use 3-dimensional constitutive equations. And that's exactly what we do. Okay, no plane strain, plane stress type assumptions. So when you go into using the strain displacement relations of shell theories, even though you start with thickness to the power 2, it ends up being, because of the curvilinear relations, all the way up to the 4th power. So we neglect those quantities, retain up to only first order kinematics, but we have also pursued higher order just to see what happens. Does it bring enough accuracy into the calculations? So I will show that briefly, but we are very happy with the 7-parameter polynomial approximation that I showed on previous slide. In other words, 3 degrees of freedom here, 3 here, and 1 stretch. That's how the 7 degrees of freedom come into picture. And I won't go into these details, but as you all know, the number of terms that you will have in a curvilinear coordinate system for a shell element would be enormous. So you have to use standard Maple or some algebraic manipulator to actually compute them. So this is the comment I just made about including higher order, which is what led to 12-parameter approximation. So we have published these papers in the literature in recent years. So we account in the shell a linear relation between the second Piola-Kirchhoff stress tensor and green strain tensor. So most of you know that second Piola-Kirchhoff stress tensor is a mathematical entity convenient for the finite deformation problems, and it is related to the Cauchy stress tensor through this relation, where F is the deformation gradient and J subscript F is its determinant. So that relation is obviously not linear. So in other words, looking back, the relation between the Cauchy stress and the green strain tensor is nonlinear. Although we are not doing anything in terms of material or properties. The C is the elasticity matrix, and we have accounted for, of course, both isotropic, functionally graded materials, and laminated structures. So the key features are that thickness stretch is included, 3-dimensional constitutive relations are used, and we use the displacement finite element formulation without bringing any reduced integration or stabilization. So how we able to overcome the locking that is there in shear or thickness is to use higher order interpolation for all variables. So I will say a few words about how we get rid of the higher order, the nodal values by static condensation, so that it becomes very efficient and demands only same level of computational resources as the traditional finite element shell elements. Okay, so I'll illustrate a couple of problems, and here is one, just a simple example to show a plate with a hole. If you were to use a higher order interpolation, the one I showed is a typical element. So this is the one element. In this case, it is the P is equal to 5, means it has 25 nodes in each element, but 9 of the nodes are inside the element. So 9 times 7 degrees of freedom, 63 degrees of freedom could be eliminated statically, and that's what this is about. So that makes the computational effort very close to same as what you need in the traditional finite elements. So I have to, looks like, yeah. So I'm going back to my pointer. So what I'm saying is you will not require additional degrees of freedom. In fact, you reduce by this action of statistical condensation by 72% of reduction from the higher order finite element degrees of freedom. So that is the key. And so, and this is just an example. I have many examples, and these are already published in the literature. So if I run this, I hope it works. So you can see, well, let me see. If it doesn't work, then I'll show you another example. Some of them are a little bit tricky. So let me explain the physics here. So I have a cylindrical shell internally pressurized. So as you all can imagine, if the pressure is large enough, it will expand even when you constrain the ends. In this particular case, I'm saying the ends are constrained. So when it is subject to pressure, the cylinder will of course expand radially out, except for the end circles. So that is what is shown on the next slide. So you can see how the ends are kept fixed, but the internally it is elongating, mean radius is increasing. So that increase in the radius has to come by the material flowing from the thickness into the circumference. So that is the point that I'm trying to establish here. So then you say, oh, what is the change? Of course, there is zero change in the ends because we fixed, but then there is a rapid change in that boundary layer. Then that change remains fixed. Of course, there is change, not zero change, but that change is rapid in the beginning, but then it is uniform. So we can plot that, and I'm just showing again, if you plot the thickness along the length of the cylinder, normalized with the length, and this is also normalized, the change in the thickness divided by the original thickness. At the edges, it is a rapid change, but then in the middle, it is uniform. So this has been kind of verified, I use the word verification, by independent analytical study by Amabile at McGill University, originally from Parma, maybe he still has a position there. So you can see that it is interesting to see the two, of course ours is computational, which is nice smooth, as one should expect. Whatever approximations made in the analytical study has a little bit of oscillation, which is not physical, but nevertheless it proves that we are on the same page in terms of ability to predict the thickness change in this shell. So now, with everything said and done, the users of such technology, they question, so if you say all this, so what? I mean, how is that going to be better than the commercially available codes? So I created this figure where I'm showing the stress. By the way, displacements really don't change that significantly. Even with the first order shear deformation theory, you can get the displacements. But most designs are based on stresses, including interlaminar stresses. So I'm just showing the plot of the stress and the intensity of the load applied. And you can see, so although it says point load, this is kind of a parameter coming from the distributed internal pressure Q. So what you see is the slide looks a little bit busy, but I wanted to see, first one is ANSYS and Abacus shell elements. Okay, so they, very well agree with each other. And then we used Abacus and ANSYS 3D elements. And those, they don't give exactly the same as the shell elements. So in the very, very beginning of that small load range, they are same. But then 3D brings things that are missing, including thickness stretch is included in 3D finite elements. So in our shell element gives results closer to 3D. So you can see not only very, all the way up here, they deviate a little bit from in this range, okay? And there, the deviation is even between the commercial codes, ANSYS and Abacus, even though it's same 3D finite elements. Obviously, there is some implementation difference. So our shell element does extremely well compared to the 3D finite elements in a good range of the load. So that tells you that we can use 3D finite elements to get the results, but they would be very expensive. Whereas if you use shell elements, it would be much cheaper. So the robustness coupled with the computational efficiency is of importance to the user community. So this slide shows the degrees of freedom. If you use 3D finite elements, this problem takes 50,000 degrees of freedom. Whereas our 7-parameter only takes 2,000 degrees of freedom, resulting in only 66 CPU. Compared to, the cheapest is Abacus because of their efficient implementation, 720. So order of magnitude difference. And when compared to ANSYS, it's even 2 orders of magnitude. So that is the point. So if you can get the same level of accuracy with shell elements, that's the way to go. All right, I conclude this and go on to talk about the non-classical continuum mechanics. And there are people that have worked with me, and their names are listed here. And so classical continuum mechanics does not account for the effect of the microstructure within the material. That means a material point has no structure. For example, we don't say that material point can stretch, rotate, and so on, but we only talk about material lines. So we have these, standard 3 displacement degrees of freedom, but in general, it can have 9 degrees of freedom, okay, at a material point. So what are we trying to do? Again, in the same way, we want to improve the classical continuum mechanics by bringing missing information for those problems that require it. So we never try to use a sledgehammer to kill an ant. What I mean is there are vast majority of the problem, I would say 99% maybe, nearly, will probably be very good with continuum mechanics the way we have. It's very small modifications. But if you want to bring the missing, the length scales that are inherent or intrinsic to material, then we have to look at those aspects. And these do make a difference in 2 problem areas. One is very small devices, micro, nano, or very large structures, mega structures. So in both cases, this non-locality has a different meaning. It's not only material. That's what Professor Bazant said. So the constitutive model is where the non-locality is brought in, but really you can bring in the structural level because it is ultimately how you choose to represent the actual structure, the problem. So you can bring when I say the structural means the inner details of a mega structure. Think of a ship structure or any mega structure that has a lot of architectural features. Think of a deck. The deck may have, depending upon the construction, the web type structure, or the web could be very complex form. And so those needs to be accounted. And let me just go back there. If depending on the architectural details, of course, in theory, it is possible to account for all of that in your finite element model, but it will lead to trillions of degrees of freedom. And even then, you may not be able to account for the intricate details of how they are attached. So we need to find a what you call computable way, realistic way, by bringing the missing stiffness information that is provided by these inner details, architectural details, including in metamaterials, into our global plate and shell theories in the form of non-local parameters. So that is other way to bring the non-locality. So I will only flash these because these are micro devices, and people like McFarlane and Colton, and also in biomechanics, they found that if you use the classical continuum mechanics, what they observe in experiments cannot be explained. For example, you see a cantilever like a beam here, you apply a point load, and we know that the deflection under that point load from mechanics of materials calculations or elasticity would be PL cube over 3 EI. But if you try to reduce the thickness from say 10 micrometers to say 2 micrometer or something smaller, then we expect it to be even more flexible. But they found that's not the case. So that means surface energy is coming into picture. When the volume is smaller than the surface area, some other effects are coming. So we must account for those. And these people have done with non-local parameter. Again, it's a modeling issue. How do you actually represent the physics? And that's where you bring these parameters. And similar observation was made by Rod Lakes of Wisconsin when he tried to subject the bone structure to torsional loads. He found it became stiffer as the diameter was reduced. Okay, so you can see the classical theory would give a horizontal line the way it is non-dimensionalized. So whereas the experiments show all those data points. So Rod Lakes used non-local theory like Mindlin's or strain gradient type theories, and he calibrated the experimental data and found the non-local parameter to be 0.09 millimeters. Okay, and then you might ask, what is that physically? Well, physically you cannot put a handle on it. It is really all things going into it to represent this non-locality is embedded into that parameter. So it's not that simple characterizing these experimentally, but you can only compare the global data. So whereas in the megastructures, it is clear we can identify physical parameter because it is a linear combination of the structure, actual structure. So you can see, so that means you have to, when you do homogenize, not in a classical sense, if you do classical sense, you get an equivalent single layer theory with equivalent ABDs. But here we do one lower. You actually calculate the stiffnesses of all those and introduce them into the non-local parameter. So we took a very simple problem here with, you can see the sandwich structure with the web core. So the main issue is I want to use the standard plate theory, except I will bring the antisymmetric, symmetric shear needed to represent the deformation, especially where the load is applied, in this case a line load. So what we need to do is connect the 3D setting to the 2D setting through constitutive model. So the main problem is to bring the micropolar theory, that means allow the rotations of material points. And that is the micropolar theory. That means you introduce those additional variables into your plate theory. But then you need to also bring the architectural details through the constitutive model. So there we go to any commercial code to understand the unit cell load displacement relations. And here is the standard displacement field, except I added 3 more rotations at a point. So these are the micro rotations, okay? And then we use the energy equivalence to introduce, put there a lot of detail here. You can read the papers we have published recently. So we relate the resultants, stress resultants of the theory, the two-dimensional micropolar theory, to the kinematic variables, strains, curvatures, shear strain, and the curvature through these ADGH. And these are the ones which will be calculated by relating or connecting the energy equivalents. Okay. So we found the results are very, very good. So here we made a comparison. When you do this entire panel with 3D finite elements, you get these blue results. Okay. And whereas if you use the 2D micropolar, you get that red, which is very, very close to the 3D results. Whereas the classical, there are two different, classical. The very, very classical one is showing a lot of singularity here, or very large value of the displacement. And also the minor modification to this 2D classical was made in another paper by Romanoff and Javaleka. They're both from Aalto University in Finland. But those modifications are very minor. But they don't produce that much a difference, as you can see. So what I'm saying is a summary that the non-locality brought in a physically consistent way by accounting for the three-dimensional effects into the two-dimensional theories makes it computationally efficient while keeping the accuracy same as that of the 3D. So here, I'm just going a little bit more details. You remember the web, it has a thickness, and depending upon the thickness, you can see the accuracy is different. So the 3D finite elements and 2D micropolar, they're always very close, unless you magnify it, okay? So whereas the classical is up there, so the error is clear. And if anything, as the thickness of the web increases, the difference may be increasing between the two. And so this is even a little bit more relative difference between the 3D in terms of percentage for the same kind of data, thickness, phase thickness being increased. So we have also done the buckling, and there it's even worse. So the classical theory does not show sensitivity to the thickness change of the web, because in the 3D finite elements, you can see that blue and the 2D micropolar theory, they're very, very close to each other. And in terms of efficiency, the 2D finite elements will be very, very cheap, less expensive computationally compared to 3D finite elements. So we have also compared the frequency. As you can see, the 3D finite elements shown in black, and the gray is the 2D micropolar, and the darker gray is the classical. So there, of course, the differences keep increasing, depending upon the frequency. Higher order frequency error gets to be larger with classical plate theory. Okay, so the last item of my planned agenda here is what I called GraFEA, graph-based finite element analysis. Okay, so what we want to do here is to use the traditional finite elements, piggyback on them, but rather bring a non-standard thinking in the form of non-locality. And I'll explain a little bit more in the coming slides. So this is the basic idea behind. So what we do with this is the strain energy written in terms of the, of course, the global coordinate system and local coordinate system. And this is the material coordinate and instantaneous. But ultimately, we can write in terms of the distances between points. So whether all of you realize or not, no matter what method you use, numerical method, finite elements, finite difference, finite volume, meshless method, all of them at the end of the day, if you remove the element personality or domain personality, it's all points. So the points is where we are determining the information. So that means this distance between ith point and jth point, I call Dij, we can write the strain energy in terms of the distances ultimately. And the change in the distances is the measure of the strains. Okay. Of course, if you go to finite elasticity, we use those stretches, all that, which is similar concept. So we have published a paper in 2015 to illustrate this using the Cauchy's representation theorem and invariance to rigid body motion, that you can write everything in a finite element context in terms of forces and strains along the edges. Okay, so you don't need to compute strain stress at every node. So why edges? Because we can use, because it all depends on your goal. If your goal is to determine damage and fracture, so these material lines have to break. So that is interesting or useful to write this information in terms of the edge forces and strains. So these are shown like springs, but really the forces in along each edge of a triangular element are shown. Then we also bring additional non-locality through this phi matrix. And even though it is shown as a diagonal here, we have implemented recently to make it as a real number, not just 1 or 0, but also it could be 0.5 or 0.6. So this is when it is 1, everything is normal. But when it is 0, it's broken. Okay. So we bring this matrix, and also this phi has a probability of failure built into it. So that is where, and phi is a very complicated expression. I will show you, because that's where you bring the non-local effects. Word non-local means it's more than that one element that is in the mesh that contributes to this phi. So the modified finite elements will be just same as before. You remember the T transpose T type, which is really most cases B transpose B. So now because of this phi changes, the stress measure is this, the force becomes this, and the stiffness matrix takes this form. Okay, V the volume. So now we are looking, if it is local, you are only concentrating, the circle is only on the circle, on the element. But if it's non-local, the circle can go larger. And that has to do with what is that you're trying to predict. Suppose if it is a metallic and the metallic structure, the circle may be smaller, still encompassing more than one element. But if it's a concrete, where you can see with the naked eye the size of the constituents, so it may take 3 times the size of a largest constituent in the concrete. And this is found, I think, if I remember, Bazanta and his colleagues also investigated, and they suggested anywhere between 2.7 to 3. So that is one of the things we have implemented in our abacus code. So when I mentioned abacus is the number cruncher, but we use the UMAT to embed all this thinking and do the calculations using abacus. So this is the detail here. I would only point out that this phi function that I mentioned before, it actually has the regularizes the effect of the microcracks. This bottom figure shows if it is a local, then you only pay attention to the centroid of the triangle. Okay, this is being a linear triangular element. We can talk about higher order too. And all these dots are the centroids of the neighboring elements. So when you put a larger radius, then you see 4 elements are in that radius. I'm counting only those elements with centroids inside the circle. So then we calculate according to the equation the average of the edge strains of all the elements participating in there. And that with some material parameter, such as the size of the largest grain size of that structure, will define the radius or phi. So this is how we bring the non-locality. Okay. So we have implemented it into Abacus through ViewMat. And so it introduces material length scale, which controls the fracture process and regularizes the modeling response. That means we get results that are mesh independent, unlike XFEM or cohesive zone models. And it also allows the use of different types of fracture criterion. We have used the strain-based criteria, but we can use also energy-based or stress. So the point estimates are replaced by zone averaged properties. So we don't use the stress intensity factor, for example. Although you can bring that as a measure into this R phi that I described, the radius of the zone. So here is an example of this is the experimental thing that you are seeing on the left. On the right is our simulation. So this problem was also covered in a paper using XFEM. It does not even converge after a few steps. And we were able to solve this without any issues. Very robust. And this paper appeared in 2019. And moving on, we have done a concrete problem where the bottom is fixed, and then we apply a point load here, as my mouse is showing you. So we are trying to predict the mixed mode fracture in the concrete. By the way, if you see the crack propagation, there is a diffuse zone, means it's not very sharp. And that sharpness can be controlled by the radius of the zone. And of course, if you use one element, you will get more sharp. But in reality, that is not what you will see in experiments. So the damage zone has finite width. It's not sharp unless it is very, very brittle material. And of course, more homogeneous, not like concrete. I'd like to close by saying that the higher order shell elements are robust. They avoid all kinds of locking. And there is experimental as well as modeling evidence that non-locality is real. It's not cooked up by mechanics people, but we can show, and experimental people stated those things. So we can bring non-locality and improve the classical continuum mechanics to account for the missing information. Finally, GraFEA, I think we are very excited. It's under continuous development. We are extending it to non-brittle materials, including even composites. So it's a very robust methodology, and we are hoping that other people get into this area and work. And we are willing to share any information for the benefit of the community. Okay, so I will say two things in closing. We must develop robust computational tools. They should not have any fixes and artificial means to get the results that you want. Rather, it should be physics-based. Of course, simplicity, robustness, and practicality are important. We also must seek physically meaningful experimental validations. Because these days, when you do very, very small object like micro, nano experiments, you still need computational effort because you don't know what you're really experimenting. So it's not just one has upper hand over the other. We have to work together. But we need physically meaningful experiments to make sure the computational people are not going tangent to the actual objective. So with those two, I will just say we have a lot to do. Okay, the time we live in this world is very short. Okay, not because I'm old, because even the youngest of all you logged into listen to me, your lifetime is a small dot in the spectrum, okay? So there's so little time, but there's a lot to be done. Take pride in whatever you do, whatever little you do, because we are not going to make Einstein contribution, but collectively we make a big change or big contribution to the mankind that helps in terms of health, other transportation, medical help. So there are many things, including, of course, defense. So I will just thank you for logging in to listen to me, and also to Professor Wenbin Yu and Byron Pipes for their invitation to deliver this webinar. So I'm ready to answer any questions. Wenbin, I'm ready.
Thank you, Professor Reddy.
Yeah.
We do have a number of questions. Some are very specific, and there's a few also general. Let me begin with one that came along early in the presentation, and it was as you were showing some of those examples of the early shell theories, whether those were custom finite elements models or whether those were implemented in Abacus and ANSYS. And there were a couple of questions, people wanting to know how they might be able to get their hands on some of these models.
Okay. So let me answer that. So unfortunately, we could not put that into ViewMat because Abacus has a limitation of 6 degrees of freedom per node. So I would be very interested in any of you interested in working with us to find a way to eliminate the 7th degree of freedom and create a ViewMat. Eliminate against in a statistical condensation method. We thought about it, but we were doing other things to explore. But there is room for us to collaborate, and so the code that we developed is all ours in-house. There is no Abacus or ANSYS results here other than for those comparisons I did. So the results we obtained with the shell element that I discussed here is all our code. There is no Abacus involved in that. Okay, next question.
Thank you. Could you comment on some of the interply physics and how that comes into this?
All right. So, because I did not want to put all those results, but we also studied the interlaminar stresses, means stresses between plies, because that is where the most of the real world failures come. If you take a panel subject to laminated panel, subject to compressive loads, they do not fail in compression. They fail in buckling, and that buckling takes place even after buckling. It may be intact, some of these laminates, but then they start delaminating. So that means the interlaminar stresses really play the role in predicting the failures. So through this element, we were able to capture those, and we compared with the results by NASA people, and they were excellent agreement up to the true failure, meaning delamination, not just initiation, but delamination. So those are also available in the literature, including in the papers. So again, you all can send emails to get references to these works. I'll be happy to provide them.
Thank you. And there were actually a number of questions of people asking for very, very specific types of questions or access to the presentation or otherwise. So we'll let them contact you for answers to those questions or to get that.
And I assume that this presentation would be available on your website, right?
Absolutely. And we will send a link to all those who have tuned in today with details to access the presentation.
Very good.
There have been some questions about the micropolar theories, you can imagine, everything from how to implement it in existing finite element codes to to more general questions of how do you choose micropolar or other higher order theories when you're considering various problems, if maybe you could comment on that.
Okay, so I think, again, I mentioned about simplicity and robustness. So the first order shear deformation theory, with the exception of the need for shear correction factor, are very good, okay, for most applications. So if you want at the most, and there is room because that has not been done yet, is to use the third order shear deformation theory. So you see this highlighted red box, it is based on the first order theory. So if you want to extend our work to third order, where you don't need shear correction factor, but on top of it, you would be representing the interlaminar shear stresses quadratically, which is a more desirable thing. Because the first order theory, even with the shear correction factor, it does not change the nature of the variation of the stresses. They are still constant through each layer. So, and the way we brought in the abacus information, you can actually create a unit cell information. And unit cell in this case is this, I web, but it could be more complicated. But the assumption here is that entire plate or structure that you're doing has one unit cell. But you can have more than one, but obviously limited in terms of computational resource, you probably don't have more than a couple unit cells, okay? That means only in the entire structure, there are only 2 or 3 different structures that you are using. And that is not out of the ordinary, because in real world also, you don't use too many, only 2 or 3 different kinds. So except for that, you don't need to use abacus. Rest of it could be your in-house code. That means your own personal research code. So again, we will be happy to help you understand the details of this, but the program that we have it only uses the information from commercial codes to determine the ABDs that I'm showing here, okay? After that, it is all your code, okay? So outside of that, that means if you want to put a view mat or something, that is possible, okay? So again, there is room for improvement in terms of the connectivity between in-house code to the commercially available code. I think I also need to address this. There are really very good question is about the parameter value. In this problem, it's all intrinsically built into the calculation connecting 3D to 2D plate theory. So that means there is no guessing here. It comes directly from the 3D information and the web structure, in this case the eye, that is there. So, but if you think of the other way is, you remember that McFarland used, and also I think in the biomechanics case, there was a parameter, but there it is not that physical, because it's an effective parameter that comes in. And if you ask where is that coming from, I don't have that slide, but it is coming in the writing the coupled stress related to the curvature. So that means if you go to Mindlin's paper, you will see that the shear modulus times L squared is connecting the coupled stress to the the curvature. So that is where the length scale is introduced, but it's only interpretation. There is no physical meaning to that L squared. It is an effective length scale.
Thank you, Professor Reddy. We've come to the conclusion of our hour together. We thank the audience and participants, and again, welcome everyone again on March 4th as we get to listen to Professor Klaus Friedrich. And you can see the schedule going forward. Again, a warm thank you to Professor Reddy, and we'll close here.